Hello everyone. So, welcome to the next lecture on derivatives. In this lecture, we will continue our discussion of finding points of minima and maxima of functions. So, let us first recall what are local maxima and minima of a function f of x. So, point C in the domain of f of x is called a point of local maxima if there exists some real number h positive such that f of c is greater than equal to f of x for all x in the open interval c minus h to c plus h. That is, f of c is the maximum value of f of x in some small enough interval containing the point C. Similarly, C is called a point of local minima if there exists h positive such that f of c is the minimum value of f of x in the interval c minus h to c plus h. So, for example, if we look at a function, say we have this function, if you look at this point, let us look at these 4 points. We call these points C1, C2, C3, C4. Then if you look at this C1, if I take this interval and if I restrict this function to this interval from C1 minus h to C1 plus h, then this f of C1 is the maximum value in this interval, even though this is not the maximum value of the function for all x. For example, this at this point C3, the value of the function is bigger. So, this is a point of C1 is a point of local maxima. If we look at C2, at C2 again if I take a small enough interval containing C2, then you see that this f of C2 is the minimum value in this interval. So, C2 is a point of local minima, and at these points if you see, the derivatives exist at C1 and C2, and here we have f prime C1 is 0, f prime at C2 is also 0. Now, if we look at C3, this point, again if I take an interval C3 minus h to C3 plus h, then the function, it attains its maximum value at this point C3. So, this C3 is again a point of local maximum, and C4 is a point of local minima. What we know is that at a point of local minima, if C is a point of local maxima or local minima, then either f prime C is equal to 0 or f prime C does not exist. Remember that we have proved this in previous lectures, that if we have a point of local maxima or local minima, and if the derivative exists, then the derivative must be equal to 0 there. Also, we have that let me write this as this is called the first derivative test. So, let f x be a function defined on an open interval I, and then we have if f prime x changes sign from positive to negative. See what happens here in this example. If we have, as we move across this C1, f prime is positive here because the function is increasing, and then the function is decreasing as we move to the right of C1. So, f prime is negative here. So, this changes sign from positive to negative, then changes sign from positive to negative as we move across C, then C is a point of local maxima. Similarly, if f prime x changes sign from negative to positive as we move across C, then C is a point of local minima. As you can see, at the local minima, f prime changes from f prime less than 0 to f prime greater than 0 as we move across this point C 2. So, this is a point of local minima, and if f prime x does not change sign as we move across C, then C is neither a point of local maxima nor a point of local minima. So, this gives us a test to find points of local minima and maxima. So, to find points of local minima and local maxima, we find the critical points that is points where f prime x is equal to 0 or f prime x does not exist, and then we use the first derivative test to determine whether those points are points of local maxima, local minima or neither. Let us look at an example. Suppose we consider f x equal to x cubed on R. So, if we look at f prime x is equal to 3 x square. So, what we get is f prime x is equal to 3 x square, thus f prime x equal to 0 if and only if x is equal to 0, that is 0 is the only critical point. Now, we will check whether 0 is a point of local minima, local maxima or neither. So, if we see this function, since f prime x is equal to 3 x square, this is positive for all x greater than 0, So, if we see across this critical point 0, f prime is positive, f prime is positive as we move from this. So, f prime does not change sign, f prime x does not change sign, as we move across x equal to 0. This means that the function is increasing and the function is increasing here also. So, in this case we see that this point x equal to 0 is neither a point of local maxima nor a point of local minima. Such a point which is a critical point, but is neither a point of local maxima nor local minima, is called an inflection point. So, in this case x equal to 0 is an inflection point or point of inflection. So, let us look at one example. Find the points of local maxima and local minima of f x, which is given by x cube minus 3x plus 3. So, we find the derivative f prime x, this is equal to 3x square minus 3, which is equal to 3 times x square minus 1 or 3 times x minus 1 x plus 1. So, first we find the zeros of f prime x. So, f prime x equal to 0 if and only if x is equal to minus 1 or x equal to 1, and then we see the sign of f prime x. So, we have critical points minus 1 1, and then we see that this f prime x x square minus 1 is negative if x is between minus 1 and 1, and if x is greater than 1, then f prime x is positive, x square minus 1 is positive, and also if x is less than minus 1, then f prime x equal to x square minus 1 times 3, this is positive. So, that means that the function is increasing, it changes sign from positive to negative as we move across minus 1, and it changes sign from negative to positive as we move across the point x equal to 1. Thus, x equal to minus 1 is a point of local maxima, and x equal to 1 is a point of local minima. Another example, let us look at g of x equal to 2x cube minus 6x square plus 6x plus 5. Here again let us find the derivative g prime x is 6x square minus 12x plus 6, which is equal to 6 times x square minus 2x plus 1, which we see is equal to 6 times x minus 1 whole square. So, here again x equal to 1 is a critical point, but we see that g prime x is positive as we move across x equal to 1. So, here 1 is the critical point, g prime is positive to the left of 1 as well as to the right of 1. So, the function is increasing and it is increasing in this interval. So, in this case x equal to 1 is a point of inflection for g of x. It is neither a local maxima nor a local minima. So, for this function g of x, there is no g of x has no local max or local min. We will later see that we can also draw the graph of this function g of x using these informations. Now, let us look at some examples. So, let us look at simply this function f x equal to x square. If we find the critical point f prime x is equal to 2x. So, x equal to 0 is the only critical point. We can use the first derivative test to see that x equal to 0 is a point of local minima, because f prime x is negative, it changes from negative to positive. So, this is a point of local minima. In fact, in this case the function is simply, the graph of this is this parabola, and the function is always non-negative and it is 0 at 0. So, it is clear that this point is a point of local minima, it is also a point of global minima. Now, if we look at what happens to the second derivative. So, the first derivative does not tell us. If we look at another function g of x, for g of x equal to say minus x square, x equal to 0 is a point of local maxima. This is f x equal to x square, and if I take g x equal to minus x square, this is g of x minus x square. Here x equal to 0 is again a critical point, which is local maxima. So, for both of these, f prime 0 is 0, g prime 0 is 0. Let us look at the second derivative. What is f double prime of x? This is equal to 2, and if I look at g double prime of x, this is equal to minus 2. So, what we see is that, so in this example, the second derivative of the function is positive at the point of local minima, and for g of x this has local maxima at 0, here the derivative is negative and is negative at the point of local maxima. Now, the question is can we use the second derivative to test whether the function is local maxima or local minima at a point. So, we will discuss the second derivative test. So, let me write as a theorem. Suppose f of x is a function which is twice differentiable on an open interval I. Also, suppose f prime at c is equal to 0. So, we have a critical point at x equal to c. Now, we want to decide whether c is a point of local maxima, local minima or neither. So, then first is, if the second derivative f double prime c is greater than 0, then c is a point of local minima. This we have seen in this example, that f x equal to x square, the second derivative is positive at 0 and this is a point of local minima. Second thing is that if the derivative, second derivative is negative at c, then c is a point of local maxima. And third, if the second derivative at c is equal to 0, then the test fails. That is, we cannot conclude anything if f double prime c is equal to 0. So, let us see first that the third condition, consider f x equal to x to the 4. and g x equal to minus x to the 4. Then f prime 0 is 0, g prime 0 is also 0. Also the second derivative at 0 is 0, second derivative of g is again 0, and if we see directly, we can see by the first derivative test or by direct observation that f x has a local minima at x equal to 0, whereas g of x has a local maxima at x equal to 0. So, what we see is that if the second derivative is 0 at a critical point, then it can be a local minima, it can be a local maxima, it can also be neither. If we consider say h of x equal to x cube, then we see that h prime x is 3x square, h double prime x is equal to 6x. So, in this case we again see that h prime 0 is 0, h double prime 0 is also 0, but we know that here x equal to 0 is neither a local max nor a local min. So, by just looking at the second derivative at a critical point, if it is 0, then we cannot conclude anything. So, if the second derivative f double prime c is equal to 0 at a critical point c, then we can have all possible cases. In such case, we may try to use the first derivative test. Now, let us look at proof of the second derivative test. So, the first case is suppose f prime c is 0 and the second derivative at c is less than 0. We want to prove that claim is that in this case C is a point of local minima. So, for this what we have to do is this we need to find some H positive such that f of C is less than equal to f of x for all x belonging to C minus h to C plus h. Now, let us look at this information that f double prime C is negative and f prime C is 0. So, by the definition of derivative, what we have is that f double prime C, this can be written as the limit, the second derivative is the derivative of first derivative. So, this is the limit of f prime x minus f prime C divided by x minus C as x approaches C. And this is the definition of the second derivative at C. Now, what we know is that f prime C is 0, but we have f prime C is equal to 0. So, the limit as x going to C of f prime x divided by x minus C, this is equal to f double prime C, and this is given to be negative, f double prime C is given to be negative, sorry, so the first case we are considering is suppose f double prime C is positive. So, this is positive, then we want to show that this is point of local minima. If the second derivative is positive, then we will get a point of local minima. So, we are given that this limit is positive. What does that mean? If the limit is positive, then that means that if I take x to be, we have this is the point C and we have some C minus h, C plus h. This means that if I take h small enough, then the value of this must be positive. So, this implies there exists h positive such that this function whose limit is positive, this function f prime x by x minus C, this must be positive for all x belonging to C minus h to C plus h. What does that mean? This means that if we look at, if x is bigger than C and less than C plus h, then this denominator C minus x minus C is positive. So, that will mean that f prime x must be positive. This implies that if x belongs to C to C plus h, if x belongs to C to C plus h, then f prime x must be positive. This is because the denominator is positive in this case. And if x is less than c, if it is in c minus h to c, then x minus c is negative and we want this ratio to be positive, then f prime x must be negative. So, what we see is that f prime x, the sign of f prime, it is negative for less than c and it is positive for greater than c. That means that the function is decreasing and then increasing, which means c is a point of local minima. So, therefore, by the first derivative test, x equal to c is a point of local minima. The second case is similar. If f prime c is 0 and f double prime at c is negative, then x equal to c is a point of local maxima can be proved in a similar way. So, in this case what we will have is that we have this limit is equal to f double prime c, this is assumed to be less than 0. If this is less than 0, then we have for x belonging to c plus h, f prime x must be negative, and for x in c minus h to c, f prime x must be positive. That means that f prime changes sign from positive to negative as we move across c. So, then by the first derivative test it must be a point of local maxima. Now, we will try to use this for a function, find the points of local minima and local maxima of f of x equal to 3 x to the 4 plus 4 x cube minus 12 x square plus 12. So, what we do, first find the critical points. So, we find f prime x is equal to 12 x cube plus 12 x square minus 24 x, and f double prime x is equal to 36 x square plus 24 x minus 24. Now, first we find critical points. For that we need to solve for f prime x equal to 0, and f prime x is 12 x times x square plus x minus 2 equal to 0, which is same thing as 12 x times x minus 1 times x plus 2 equal to 0. So, x is equal to 0 or 1 or minus 2. These are the critical points. Now, we use the second derivative test. So, we need to find the second derivative at these points. So, now f double prime at 0 If I put x equal to 0, let me write down what is f double prime of x. This is 36 x square plus 24 x minus 24. So, f double prime of 0 is equal to minus 24. This is less than 0. This implies x equal to 0 is a point of local maxima. If the second derivative at a critical point is negative, then we have local maxima, and f double prime other critical points are 1 and minus 2. So, f double prime at 1 gives 36 plus 24 minus 24, which is equal to 36, which is greater than 0. This implies x equal to 1 is a point of local minima, and f double prime at minus 2 is equal to, so here we can factor out 12, and then we have 3 times minus 2 squared plus 2 times minus 2 minus 2, which is equal to 12 times 3 times 4 is 12 minus 4 minus 2, which we see is positive. So, this implies x equal to minus 2 is a point of local minima. So, x equal to 0 is a point of local max, and x equal to minus 2 and x equal to 1 are points of local min. We can also use this to find what is the minimum value and maximum value. So, then if we look at the value of the function at these points, so f of 0, this is equal to, if you look at f of x is this, so f of 0 is equal to 12. So, this is the value at local max, and f at 1, if you calculate, this is 3 plus 4 minus 12 plus 12, this is equal to 7, and f at minus 2, if you calculate f at minus 2, this turns out to be minus 20. Okay, so, the next one I will show you the example that we have considered before. So, consider f of x equal to x plus 1 by x, x not equal to 0. Find points of local minima and local maxima. So, here like we calculated that first derivative f prime x is 1 minus 1 by x square, and this gives x equal to plus minus 1 are critical points. Now, if we calculate the second derivative f double prime x, this is equal to, this is minus x to the minus 2. So, this will be 2 by x cube, and then we see that f double prime, if I evaluate at 1, this is equal to 2, which is positive. This implies x equal to 1 is a point of local minima, and if you calculate f double prime at minus 1, this comes out to be minus 2, which is negative. This implies x equal to minus 1 is a point of local maxima, which agrees with what we have seen before, that the graph of this function looks like this, and at x equal to 1 we have a local minima, this value is 2, and at x equal to minus 1 we have local, at x equal to 1 we have a local minima, and at x equal to minus 1 we have a local maxima. So, with this I will stop today. In the next class we will see some more applications of derivatives. Thank you.